Now, we are pleasure to introduce our next speaker, who is not only top-level optical engineer, also actively involved in supporting and mentoring the student chapters of Optica, in addition to collaborating with Astronaut Scholarship Foundation. Welcome, Ben. It's an honor to have you with us.
Hi, great to be here. Thanks for having
Eh,
me.
Are you okay if introduce your biography and your abstract of your presentation?
Sure. Go
Yes.
for it.
Okay. Dr. Benjamin Cromey. It's a principal optical engineer at BAI Systems Inc., a space and mission system in Boulder, Colorado, formerly known as a Ball Aerospace. He received his PhD in optical science from the University of Arizona in 2020. He served as optical design and analysis lead on the Roman Space Telescope Wide Field Instrument at BAE Systems, as well as the responsible engineer for the 8 filter elements on the instrument. His current work includes exciting R and AMP efforts to prepare for the NASA Ability World Observatory. He has authored more than 30 publications and actively serves the scientific community in a variety capacities across space, optica, and the Astronaut Scholarship Foundation. The title of his talk is The Roman Space Telescope Wide-Field Instrument will enable revolutionary advance in astronomical survey science. Instrument sensitive spans that 0.5 and 2.3 micrometers spectral range with a significant increase in field of view. Detector sensitive and angular resolution compared to exciting observatory. The science of the observatory drove tight stability requirements and necessitate an array of different optical elements with WFI to switch between imaging and different wavelengths, and using two slitless spectroscopy elements. The science also drove the need for an uncommonly high level of detector calibration, requiring an onboard calibration system supported by unique optics as well precise straight light mitigation. In 2024, WFI complete its year-longer integration and test campaign as a full instrument, including multiple environment tests, enable its performance to be studied in operation temperature conditions. This presentation summarizes several key optical performance aspects of the instrument and how they were verified, including bandpass filter, wavefront error, stray light control, and optical mechanic alignment. The results demonstrate that the WFI is ready to help transform astrophysics as a part of the next NASA flagship observatory. Thank you again, Ben, and let's proceed, please.
All right. You guys seeing my screen okay?
Yes, we can see.
Okay, great. All right. So thank you for that great introduction. Happy to be here once again, and we'll get into about Roman. So NASA has made a series of what are called these flagship observatories. And the reason that NASA makes these is because they're trying to answer a fundamental question about the universe, a question that is so difficult that has perplexed astronomers for so long that the only way that we know of to answer it is with these very expensive, complicated missions. That's the reason why they're worth being so expensive and so complicated, is because that's it's the way to answer these hard questions. So the most famous of these certainly is Hubble, which amazingly is still working after 35 years in space. Hubble was looking to answer, after its namesake, Edwin Hubble, trying to understand what the rate of expansion of the universe is. And certainly since then has done so much on understanding the galaxies and stars and so many other features about the universe. After Hubble came the Chandra Observatory, which is an X-ray observatory. So it's studying high energy phenomenon and how those affect the formation of the universe and galaxies. Also still working after 25 years in space. Spitzer, the only one of these currently not working, but still has storied history of 20-ish years in space, or about 20 years in space. This is an infrared observatory looking at how planets form with the distributions of gas and protoplanetary disks that form around stars, and how planets come from that. James Webb, also very famous, especially because it's launched so recently, is looking at understanding the formation of the universe using really fairly long infrared wavelengths to stare back into cosmic history and figure out how those evolved over the course of time. And like these other observatories, it's going to do all sorts of unexpected things. It's turned out to be great for black hole science. The black hole scientists are loving it, which was not a key science case when it was proposed. And now we get to Roman. Roman is aiming to understand the confusion of dark matter and dark energy. Dark energy being, why is the rate of the universe's expansion increasing? It would seem that that would require some form of energy increase that we don't understand. Otherwise, why would it be speeding up? So that's the mystery of dark energy. And dark matter, why is the universe clumpy instead of evenly distributed? What is the stuff that is making it more dense? What are all of these supermassive objects that we can see the distortions they do to light as though it's passing around a gravitational lens, but we can't see an actual object? And Roman is also going to do a big survey of exoplanets. We have had missions like Kepler or TESS that capture a whole bunch of stars and examine for exoplanets there, but those missions have only looked in really small portions of the sky. So if you had a really wide field of view and you could look in more places, how many exoplanets would you find? So each of these great observatories was recommended by a decadal survey. So the astronomy community comes together and they tell NASA and other funding agencies how to prioritize their science funding for the next decade. You can see the dates above each of the observatories when they were recommended, including the more recent Habitable Worlds Observatory, which we'll talk about briefly at the end of the presentation. And we're very fortunate at BAE Systems Space and Mission Systems to have had a role in all of these great observatories. Every instrument that's on Hubble right now was made by us here in Boulder, Colorado. And the primary mirror and the supporting actuators and stuff that aligned all those mirrors for James Webb was done by us. We were known as Ball Aerospace until 2024 when BAE Systems purchased us and we became Space and Mission Systems. And I don't think it's too conceited considering our history that we should hopefully have a role on the Habitable Worlds Observatory, but we'll mention that at the end briefly. So the layout for this presentation is we're going to go into some of the science objectives for the observatory just to make sure everyone's up to speed on what we're trying to accomplish. The science objectives is the real spicy stuff, and then we engineers come along at the end and help the scientists do their stuff. So we're going to talk about the wide field instrument, which is the primary science instrument for the observatory, which is something that we made in partnership with our NASA customer. And we'll talk through filter performance. We'll talk through predictions of performance in space. And then we'll talk about calibration, a little bit about straylight, and a little bit about optomechanics before wrapping up with where's Roman now. So we'll get straight into Roman science and the observatory overview. So as mentioned, this was selected in the 2010 decadal survey. The mission is named after Nancy Grace Roman, an accomplished astronomer, the first female administrator of NASA, and considered the mother of the Hubble Space Telescope. So give her a read on Wikipedia if you're interested in her impressive career. Originally, it was going to be a smaller, unobscured telescope design, about 1.7 meter primary, but there was a primary and secondary mirror donated from a classified mission that enabled it to become an obscured 2.4 meter design. It's the same primary mirror size as on the Hubble Space Telescope. And this quote on the screen is from the decadal survey, New Worlds, New Horizons, that recommended Roman as the main science mission, talking about how this larger version of the observatory is going to be really key to accomplishing the science missions of New Worlds and New Horizons. Like Hubble, the observatory is about the size of a city bus. So you can see all of the major components here. The majority of Roman, actually I have a tiny 3D printed this. There we go. Here's my 3D printed Roman keep handy for emergencies just like this. So on Roman, there are not only some of the parts of it are deployable. You can see the deployable aperture cover on the top in my hand here and in the slide deck that kind of extends outward. The solar panels on the back are folded flat against the observatory body. And then the antenna on the back also kind of folds out from the back part here. Otherwise, it's not deployable. It's very important for Roman that it's very structurally stiff for the science objectives, as we'll talk about. So too many deployable things makes that really hard to do. The coronagraph instrument is on the other side from us, the wide field instrument. We're over on this side, and then CGI is on the other side. CGI was made by Jet Propulsion Laboratory. That's doing some really interesting exoplanet detection stuff important for HAB worlds. The field of regard, or the region where Roman is looking, is kind of perpendicular to the plane of the solar system. It's going to kind of be able to look above and below that plane and do these really wide surveys. Now, why Roman? So Roman sees in wavelength bands that both Hubble and James Webb can already see in. So why did we need to have Roman in addition to observatories that can already survey the same 500 nanometers to 2300 nanometers band? Well, the reason why is because Roman has a humongous field of view. It's got an over 100 times increase in field of view compared to Webb and Hubble, and that makes it a survey mission. So rather than Hubble and Webb, which are going to look in super gory detail at really tiny, tiny little things, Roman is going to look in really large swaths of the sky at once. And that is going to enable scientists to do really big data and analytics on the sky and use advanced machine learning and AI tools to help pull out all of these dark matter, dark energy things from the background. Roman is projected to do 20 terabytes a day worth of information with its 300 megapixel wide field instrument. So it's going to be a lot of information coming down at once. I don't know about your computers, but I can't deal with 20 terabytes a day coming into my computer. So the most of the processing is going to be in the cloud that researchers will have access through Amazon Web Services to get to these large data sets. On slide deck. There we go. So the core science missions for Roman are the high latitude wide area survey. This is going to be just kind of capturing as much of the sky at once, a significant portion of the sky. And this is over the core 5-year initial mission for the observatory. It's going to spend quite a bit of time doing this. This is covering pretty much all of the main science objectives of the observatory. You can see on the bottom there of understanding dark matter, dark energy, galaxies, transient objects, solar system. The high latitude time domain survey is looking at the same region again and again. Transient events like supernova are really helpful for understanding the expansion of the universe because certain types of supernova have very regular amounts of brightness, which makes them a really good marker for distance. So returning to the same field and checking it over and over again for supernova is going to be very useful. There's also the galactic bulge time domain survey, which is looking at the center of our own Milky Way. This is going to look for transiting exoplanets over stars, as well as using gravitational microlensing to see these planets. All right, so that's a lot of the science objectives. What does that mean for me, the engineer who helped make it? So the telescope needs to be able to switch between imaging and a slitless spectroscopy mode in different bands. So that necessitates that we're able to have the telescope change which wavelength it's looking at, and it has to be very, very stable element to element, because when the scientists want to change wavelengths, they don't want to have to refocus the observatory or anything. They need to look again and again and again and be very quickly. The galactic bulge time domain survey, for example, if you saw the timeline on this, we're looking in the same area every 12 minutes. So as we move around and take pictures, we have to repoint and take pictures fairly quickly. Both Webb and Hubble especially Webb with all of its deployable, flexible structures, kind of vibrates around a lot when you move it. So we have to be a lot more stable than Webb is. The detector also has to be one of the most precisely calibrated detectors that's ever flown, because gravitational microlensing affects, micro is in the name. It's very small distortions to the light from these bright objects. And in order to know what is actual useful distortions and what is just your point spread function being messed up because of a small distortion in your observatory, that's very important. Because we're an infrared mission, thermal self-emission is really important. When things are hot within the telescope, they can be light bulbs to the infrared. So we don't want to have a big problem with our signal to noise ratio being messed up by warm objects within the telescope, making it the detector. And then finally, this thing's going to be in space for a long time. We have to be able to deploy it when we launch from the ground to get into best focus. But the observatory's performance will shift over time. And we need to be able to compensate for that and adjust for best focus over hopefully a similar 20+ year lifetime for Roman in space. So let's get into the wide field instrument and the overview. That's actually me in the clean room garb there, looking at the filter elements. It's kind of weird to know these optics as intimately as I do, because I spent years of my life following them through the design and integration and test and assembly and final verification that we're talking about in this presentation. So I know those optics very, very well. So we'll get now into the optical details for the observatory. So we share the field of view with the chronograph instrument that I mentioned earlier. So we never actually see the same thing at the same time as CGI, but since we're kind of looking around and taking a lot of pictures at once, we'll capture the same area in different individual pointings at the observatory. So we're kind of tucked off to the side. If we strip all of this and mechanical stuff away and just get into what the Code 5 model of the observatory looks like, there's 5 mirrors optically upstream from us in the wide field instrument, 3 of which are powered, 2 just for packaging, and then the wide field instrument is that box on the right of the screen. And the filters are towards the front, and then our very large focal plane is towards the back. Now, the wide field instrument is the primary science instrument, as I mentioned. So all of those objectives for science rest on us. This was made in concert with NASA. So we made what's a component subset, which is most of the instrument, called the wide field optomechanical assembly. And NASA provided a few of the components that I'll list out here. So the radiator panels on the back are what is physically exposed to space and helps to keep the instrument well regulated in temperature. The ACM, the alignment compensation mechanism, is what it moves the detector in and out of focus to maintain best performance for the observatory. The optical bends provides most of the stability for the instrument. It's a fancy composite structure that's very, very stiff and thermally stable. The COBA is the cold optical baffle assembly. It's a set of vanes at a colder temperature that help to give good stray light performance to the focal plane. The aperture cover is just a part of the thermal and physical enclosure for the instrument. The latches are the physical connection between the instrument and the rest of the observatory structure. The element wheel assembly, which is where we'll spend most of our presentation talking, since that's the core of the optics of the observatory. That's where those filters, that was the element wheel assembly in that picture of myself and those filter elements that we saw just a bit ago. NASA provided the focal plane electronics and the focal plane as components to the wide field instrument. And the simplified relative calibration system, or SRCS, is the source of internal calibration light for the instrument. CAD models are cool, but pictures are much cooler, of course. So these are the actual pictures of the wide field instrument on the left. It's surrounded by all this wrinkly stuff called multi-layered insulation, or MLI, to help with the thermal stability of the instrument. There's the element wheel in the center again, now mounted into the bench of the instrument. Filter F106 is one of the filters, and that's it by itself. And there's a couple of key components on the filter that we'll talk about throughout the presentation. The filter mask, the LOLO, the lamp on, lamp off diffuser, which is part of the calibration system. And there are these little shiny alignment fiducials kind of surrounding the filter mask. Now, for the geometrical optics fans in the audience, the filter sits near the exit pupil plane of the observatory. So even though the filter has this central obscuration and these little support struts, they're actually the same shape as the supports for the secondary mirror. So any light that is hitting the central obscuration on the filter mask is not science light because that light has already been blocked by the secondary mirror support. So you can see this a little better if you look at the actual observatory picture, but okay, hold on, this is upside down. Let me fix this. There we go. My animation didn't work, but anyway, so yes, that's the actual front-on view of the observatory, and the filter falls within that shadow. So there are these 8 science filters, as I mentioned. These select the key bands of interest for the scientists. The scientists defined where they want these bandpass cut on and cut off wavelengths to be. You can see the filters on the left before they were installed into the instrument, and the graphic on the right shows 2 views of the filter bandpass. The top view shows the actual transmission data for each of the filters, but because several of the filters overlap, it's a little hard to ingest it. So if you look at the graphic on the bottom is showing the regions above 90% transmission. Most of the filters have about a 300 nanometer bandpass, with the W146 filter having over 1,000 nanometer bandpass. Now, these filters' transmission behavior looks very simple in that last graphic, but it's very complicated because these filters are very large as filters go. They're over 100 millimeters across. They're slightly curved because they're in a focusing beam. You'll get better performance if you have a curved surface in a focusing environment. So that's more challenging. There's a huge angle of incidence range because of the wide field of view of the observatory. So all of this leads to very complicated transmission behavior. And our NASA colleague, Eric Switzer, wrote a paper on all of the complicated calibration efforts that we did to really understand how the filter transmission changes as a function of spatial position on the filter, angle of incidence, and a bunch of other factors, which you can kind of see in this graphic here. So that is due out soon in applied optics. Now, the wide field instrument has a very large focal plane array. It's got 18 mercury cadmium telluride detectors, H4RG, each one being 496 by 496 pixels to give us our full large field of view. You can see their layout here. Don't ask me why they're numbered this way. This is how they came numbered from NASA, and we're sticking with it. But you can see this focal plane is quite large. You know, the total width of this area is over 280 millimeters across, so quite large. This is the actual assembly of the focal planes altogether coming from NASA. If you're wondering why in this graphic there's a slightly larger separation between the top row and the middle row of focal planes, it's because of these little, the readout circuitry has to be on one side of the focal plane. So the readout circuitry kind of falls in between that top row and the middle row. And there are these little black covers over them to help with stray light rejection. Okay, so that's all of the definition for wide field. A lot of what the paper that this talk is based off on in that's been out for about a month in SPAE's JADIS journal is about the work that we did to verify that the wide field instrument was going to meet its performance requirements in space-like test conditions. So this picture is of our aptly named Titan chamber. The Titan chamber, you could park a semi-truck in. Let me see if I can do some live conversion to kilograms here. It's about it's 700,000 pounds. So divide that by 2, 350,000 kilograms-ish. Well, probably more like 320,000 kilograms. So very, very heavy. And it had to be welded in place. And this is what we did our thermal vacuum testants. We suck all the air out. We cool it down to space-like temperature conditions, and we test performance. So getting into some of the requirements. So as I mentioned, when we switched between filter elements, we could not affect the observatory imaging performance. As you rotate filters into place, into the top position, you have to be able to start using it very quickly. So this required each element to have less than, 32 nanometers RMS wavefront error. When it's in the observatory, it has to have less than 55 nanometers RMS if we pretend the observatory is perfect. That's just kind of how our requirement was written. And then all of the elements have to be confocal to each other within 30 microns. You can see on the bottom how that requirement is defined of kind of this plus or minus 30 micron region around focus. That again is because we don't have time to refocus the observatory when we're taking pictures. It has to rotate into place and immediately be usable. Now, we had tested all of the filters individually prior to assembly into the instrument. We tested them before they were coded, we tested them once they were coded, and then we tested them assembled into the element wheel, and also in space-like temperature conditions. However, 4 of the filters don't pass normal interferometer wavelengths like 633, 1064, 1550. So we didn't have measured data on their performance in space-like temperature conditions. So in order to do this in the chamber, we had to do this another way. And this was using an optical simulator and something called phase retrieval. So what the simulator does is that it imitates the wide field of view of the wide field instrument with the same f8 focusing cone of the observatory. And the simulator we could either adjust focus with the actuator mechanism, or we could adjust focus with the source tool, the stimulus of optical ray cones that we call source. So source is much faster at refocusing, and because it's not a flight mechanism, we don't worry about using up the lifetime of the mechanism, so we could refocus with source. And as I mentioned, source is it could simulate the wide field of view, so it did that one angle at a time on a big 5-degree field of freedom positioner to hit all of the points on the focal plane. And phase retrieval is the method that we use to do this. So what phase retrieval is you take in and out of focus images on a focal plane. You then do a bunch of math with Zernike's to fit those in and out of focus images with Zernike polynomials to figure out what your image quality is. And phase retrieval is how we found out what was wrong with Hubble when Hubble was initially launched. If you've not heard of this, it's one of the most famous mistakes in engineering. Hubble's initial launch, the company who made the primary mirror, which was not us, we're the ones who fixed Hubble, actually. The company who made the primary mirror gave it the wrong prescription, and we had to figure out what was wrong with it. And we used phase retrieval to do this. We took in and out of focus images on Hubble and did some math and figured out what was wrong. Phase retrieval is also how we commissioned James Webb, with aligning all of those 18 mirror segments on Webb to give us the beautiful image quality we enjoy today. So here's some hardware pictures of source and wide field instrument. This is also a good chance to see how big the wide field instrument is compared to a person. Source isn't very interesting to look at in its packaged form because it's in a big box to thermally isolate it from the wide field instrument. But you can see kind of a hole in the graphic on the left where the light is coming out from. That will then focus into the wide field instrument once they're on the trolley together. And this trolley is the same trolley we saw people pushing into the thermal chamber earlier. So what the phase retrieval algorithm does is we start with these images in the top row. These are the in and out of focus images. And then the algorithm solves for the wavefront error and returns this bottom row, which is the reconstructed images, which hopefully looks nearly indistinguishable from the top row. And we use the Zernike terms to predict the wavefront error of the observatory. Now, NASA did a lot of work on the front end to enable us to subtract source's contribution of wavefront error, because it obviously has its own wavefront error. So we could subtract out its wavefront error from the data set and leave only the filter pupil maps, which you can see some of these below. These thermal vacuum campaigns were over 2 probably about 4 months in total, and many optical tests. So there's tons and tons of data from tons of different wavelengths and tons of different angles. So I'm obviously only showing a very small subset of all that information here. The other thing we can do with this phase retrieval information is we can solve for the best focus information. Um, the Zernikeys give us a way to create what's called an influence function on computing where along focus the best wavefront error performance is. And this is how the scientists will commission Roman when it's launched. They'll do this phase retrieval process. They'll solve for the best focus position at each of the points along the focal plane, and then they'll reposition the focal plane using the ACM to the best focus position. This is visualized in this graphic here. The red arrows are indicating where data was captured on the focal plane and the direction that the focal plane needs to move in order to be in best focus. And the length of the arrow is the magnitude. It looks like a really big tilt in this graphic, but remember this focal plane is huge. So if the scale in these three axes is very, very different. So this particular adjustment is actually very small, but it looks large because of the difference in the Z scale. There we go. So doing this kind of stuff over and over again, we could see that all of the filters met their confocality requirements of plus or minus 30 microns. And, some of them are close to the edge, but being within that line is all that matters in requirements. So all of our, very satisfying to meet our confocality performance requirements for all of these filters. The final requirement on wavefront error required to simulate in the nominal observatory model. So NASA provides a Code 5 model of the whole observatory. Obviously, those be small disturbances to the observatory. The wavefront, the surfaces won't be perfect. They'll be slightly misaligned from each other. But for the sake of this requirement, we were to put the imperfect filter into the perfect observatory model and see what the resultant wavefront error would be. So the process is to load in all of the measured data that we have on the filters, remove sources wavefront error, and then turn that into a Zernike surface in Code 5 so that kind of contains the perturbations of the filter. Then we load this into Code 5 and we use it to make a whole bunch of computations about wavefront error and focus and adjustments, and then save all that data out to MATLAB and then make a bunch of cool graphics that I'm about to show you. So we did this at 3 different locations. We looked at the nominal best focus position for the perfect observatory. If you've spent this whole presentation wondering, why did they put the focal plane in that funky curve shape? This is the reason why. The shape of the upstream observatory gives us our best performing wavefront error in this curved shape. And since you want to you're going to have to do a bunch of pictures all over the sky anyway, you might as well match the curvature of the best focus or the best wavefront error performance. So this is at the nominal focus of the observatory. Then we let Code 5 adjust to put each as-built filter model into its best focus position. And then once we've done that for all 8 filters, we then average that best focus position, and we put all of the filters at that average best focus because that matches the ConOpt for how this is going to be used, concept of operations, for how this is going to be used in orbit. And once we do that, we can see that the filters meet all of their imaging performance requirements. All of the best focus positions fall within that 30 micron range. And when we evaluate them at the same focus position, they all fall below the 55.2 nanometer RMS position. So the filters are all going to do great science on orbit, which is very exciting. So now we're going to switch gears to calibration. So as I mentioned, the observatory needs to be exquisitely calibrated in order to sense these really, really small disturbances from gravitational microlensing. And to do that, there's 3 onboard calibration modes. The SRCS, the calibration system, kind of sits towards the bottom of the wide field instrument and projects light upwards and then off of diffusers built in the element wheel and reflects that light onto the focal plane. And this is doing 3 types of calibration: flat fielding, classical nonlinearity, and count rate nonlinearity. Now, the two diffusers that enable this, if you spent the whole presentation wondering, why did they put a blank aluminum thing on the element wheel? Well, it's only blank on the space-facing side. On the inside, it's this stuff called spectralon, which if you've not heard of it, is a beautifully uniformly reflective material, about as close to a true Lambertian thing as you can get. And that will uniformly illuminate the whole focal plane for really nice calibration. And then the lamp on, lamp off diffuser, which we saw introduced earlier, is hiding behind the filter mask. That's this little penny-sized object with this little cloverleaf coated structure on it. The structure there is to make space for the little mounting clamps that grab around where there's not gold coating. And this is for the count rate nonlinearity. Now, I didn't know what count rate nonlinearity was prior to starting this, so I'll walk you through it. So basically what this does is it makes it really hard to know the true flux of sources when you have differing brightness backgrounds. If you have a star of two stars of equal brightness, they should create the same flux on a detector and thus the same digital count read out from the focal plane. But the surrounding brightness around that star can affect the signal that you get. So what the LOLO does is, say you've got a signal where you have two stars of equal brightness, but they've got different background amounts. That's the science light there on the bottom. What the LOLO does is it adds a uniform illumination across the focal plane to all points. So this kind of simulates an impact of a brighter background, but it does it everywhere. So then we get the summation of those two sets of information, and we can compare our knowledge of the LOLO brightness and then our knowledge, our measured data of the science light and the summation, and do a bunch of math, and you get the calibration factor for count rate nonlinearity out of that. What the LOLO does basically is to, as I mentioned, uniformly illuminate the whole focal plane, and then it has to be very uniform and smooth. So the peak to valley ratio of brightness across the focal plane had to be less than 4. And the really tricky one is that the pixels had to be less than 0.05% different pixel to pixel, which was our most stringent requirement for the LOLOs. So that's the kind of graphics you're going to see. So keep that in mind, peak to valley and pixel to pixel comparisons. So what this graphic on the left is showing is a data set from the focal plane using the FO62 LOLO. We use the FO62, the shortest wavelength filter, because the shortest wavelength is most challenging from a diffraction standpoint to be very uniform. So the graphic on the top is the whole focal plane, and then there's two dashed lines that you can see the cross sections plotted below. There are some interesting features. The bright spots on detectors 9 and 18 are a known stray light artifact, where light is bouncing off some of the shiny features in the element wheel and coming back on the corners. That looks like a really sharp feature that you would think would break our smoothness requirement. But if you look at the x-axis on this graphic, you can see that peak is occurring over thousands of pixels. So if we add this graphic on the right, which this is doing a pixel to pixel subtraction comparison across the total focal plane, the pixel to pixel subtraction in this graphic, you're now seeing that even though these peaks, there's a slight bump up, they're still well below the requirement, because again, it's happening over thousands of pixels. We also did a lot of tests on ensuring that we meet our peak to valley requirements. I tested these at the component level prior to them being installed in the instrument. And I also tested them as in the FO62 assembly, which is, you can read about in a proceedings paper from SPIE. But then in the two thermal vacuum campaigns, we measured them a whole bunch of times, and they are well below their peak to valley requirement of 4. Okay, moving on to a few other topics before we start to wrap up. And we did some stray light model testing. Stray light modeling is really, really difficult because there's a lot of subtleties to the performance of stray light, from the final texture on a machined part from the tooling pattern, or slight changes in orientation in that multi-layered installation I mentioned earlier that make getting absolute accuracy in your model very tricky because it depends on so many subtle features. So we did some model correlation where we predicted what amount of light we would get on the focal length with this black body test. And then we actually measured it and compared those results. So the black body was put in front of the wide field instrument, which you can see in cross section in the CAD model here. And then we ramped that up from 220 to 270 Kelvin. 220 Kelvin is the hottest object that the instrument can see. So anything above in flight. So 270 Kelvin is an overtest, but it's good to do overtests because it's good to see the edges of performance. This is a busy graphic, admittedly, but this is showing the black line is that predicted data set that we did with straight light modeling, and all the red lines are the measured data from each of the 18 detectors. And you can see in general, we actually did very well at meeting our model prediction matching reality. Most of the time we were conservative even, which is great. It's always better to be on the side of being conservative than otherwise. Onto optomechanical performance. Another tool that was in the source instrument was a pupil imaging camera for helping checking element centration. So those little fiducials I mentioned earlier, we're comparing those to something called the Master Alignment Target Fixture, the MATF, where we did a whole bunch of very involved metrology to know exactly where the MATF was. So we could compare pictures of what the MATF looked like, the filter on the other side, and what we saw from source. And as source moved around, we could see the different perspectives because the MATF was a fixed location. The wide field instrument was also fixed, but because they were separated, we could see a different angle between them as we looked at different perspectives, which was very helpful to ensuring we posed consistently. And just as a reminder of what those fiducials look like, these are kind of a zoom in back on that filter mask image we saw earlier in the presentation, these little shiny spots. So we took all these pictures and then we did a whole bunch of math to predict where it's going to land in orbit, which, as you can imagine, is kind of awful math because you're doing this really complicated change in temperature from ambient conditions to space-like conditions. So being able to do this in space-like conditions here after installing in ambient conditions is very important. So alongside a whole bunch of structural and thermal analyses, we were able to predict where these elements fell on orbit. And once it's finally installed into the observatory, and we had a requirement of how similarly placed these masks had to be relative to each other. And we did great, even within our 2 sigma error bars, all falling within that requirement boundary was a very satisfying outcome. We also predicted the final flight positions of the filter elements themselves, which interestingly enough, this is a rare time where the mechanical alignment tolerance was tighter than the optical alignment tolerance because the filters are such gentle meniscus curved optics. They really wasn't a very strict requirement on where they were placed. And finally, the alignment compensation mechanism needed to be really well installed because it's a hexapod. So if you're not familiar with hexapods, it's sets of 6 actuators that as they move together, they can produce all 6 degrees of freedom worth of motion. And you don't want to waste a bunch of actuator stroke length trying to center things. So it had to be well installed. And this was also effectively installed, which is great. Okay, so moving on to where is the wide field instrument now? You can see this picture on the left is shortly after its install into the observatory structure. So Roman is starting to wrap things up. It has gone through a big thermal vacuum campaign, and then it's going to continue to be worked on and examined as they prepare for its launch next year. On paper, it's launching in October of 2026, but to some respects, NASA is a little bit ahead of schedule, so they may launch even earlier than that. So we'll have a new set of eyes on the universe very soon, which is very exciting. We had our 2 thermal vacuum campaigns, first in the fall of 2023 and then in the spring of 24. That's where all the data that I presented to you today was from the second thermal vacuum campaign. And then, yeah, we gave that off to NASA. It's been out of my life for more than a year now, but it's never left my heart. This is a video from the install of the wide field instrument. This is obviously sped up. It's kind of stressful to watch something you spent more than 4 years of your life on, suspended by a crane, but the people at NASA are very experienced and they've done this a bunch of times. So no major issues on the install, very successful integration into the rest of the observatory. This is the same really big clean room that Webb was also integrated and tested in many times. This is a video from a vibration test. We always shake things half to death before we send it into space to make sure it's going to survive the launch experience. So you can see things kind of wiggling around. There's a couple good views of the wide field instrument in most of the cameras, and then the chronograph instrument on the bottom left. So the wide field instrument is ready to be a fisheye lens on the universe. All our tests passed at BAE here in beautiful Colorado, and we are ready to send it off to NASA and integrate it. It's now there, and WFI, through its wide field of view, stable performance, and onboard calibration and compensation mechanisms, ensures it's going to do well in orbit for many, many years. Obviously, I could not have made an instrument this complicated by myself. This plaque on the right has about 1,000 names on it, and that is actually installed into the side of the instrument. The plaque's probably about yay big. And so, yeah, my name is going into space on the side of a space instrument. And if there's aliens out there and they give out parking tickets, hopefully they don't pick my name at random. The larger optics team at BAE is on that top left there. Obviously, a lot of wonderful people at Goddard Space Flight Center at NASA that we worked with, as well as folks from other organizations. So I teased this at the beginning of the presentation, that every NASA flagship mission continues to pursue a fundamental question, and the next one is trying to answer a really long-standing question: is, are we alone in the universe? The Habitable Worlds Observatory is aiming to directly image Earth-like exoplanets, and we're at a really exciting phase of that mission right now because we're doing all the initial designs and trades. The three CAD models that you see in this are potential designs for the observatory that NASA wants the broader community to examine and give feedback on. And I've been doing R&D on this for more than 5 years now. I gave a presentation at San Diego on where we're at on this project, so you can take a look at that if you're interested. And finally, I'll leave you with this. This is a simulated image of the galaxy with the wide field instrument, capturing tens of millions of galaxies in a single field of view at its 300 megapixel resolution. So thank you so much for listening. I saw some questions popping up as I was presenting, so I look forward to taking your questions.
Thank you really much for your excellent presentation, Dr. Ben, and for all you share with us. We continue with the questions. The first, for students aspiring to work in the space optics or astronomical instrumentation, what advice would you give on gaining practical experience?
Yeah, so it's hard. It's gaining practical experience really involves just getting into the lab and doing stuff. Certainly, internships are a great way to do that. The difference I find between students who have had an internship and the ones who haven't, when they work with me, is really striking. So definitely get out there and get yourself an internship, because that will really help with in any industry, but especially in space stuff.
Thank you. Have a question in the chat. How did your team ensure the alignment remained precise under operational temperature condition?
So yeah, I talked about this a little bit in the presentation as to the horrid thing about space missions is that you have to install things in ambient conditions and then prove that it ends up where you meant it to be in space conditions. So you have these horrible spreadsheets or horrible MATLAB scripts doing 3D coefficient of thermal expansion calculations to make sure everything ends up in the right place. So it's it's a lot of coordinate systems to keep track of. Um, I see there's a second thing on that question about unexpected results during the environmental test. There were some stray light leaks in some of Goddard's components, the slitless spectroscopy elements that we added an additional little blocker to those elements between thermal vacuum tests to decrease the light leaks.
Thank you. Another question for Wilmer. Can you explain in simple terms what makes the wide-field instrument of the Roman Space Telescope unique compared to previous space telescopes?
I think the thing that makes WFI unique is its overall stability for the mission. It's very important that WFI remain very stable for those gravitational microlensing, and the onboard calibration is also very unique. Having a filter wheel is very common for these instruments, so that the curved, really large, high angle of incidence filters are unusual. So they're very complicated filters. Our coding vendor took on a very challenging coding project when they accepted these.
Thank you. Another question. How do you see the future of optical engineering evolving in terms of accessibility and global participation?
Yeah, I mean the global optics community is my favorite part about being an optic ambassador is just getting to meet great folks like yourselves and to hear ideas from the broader world. I think these really challenging optics problems like this are going to increasingly require international collaboration because these these missions are very complicated, and all the challenges of advanced data centers and um, we need a lot of ideas from around the world. Absolutely.
Thank you. Daniel, question. How has working on international teams like NASA projects influenced your perspective on collaboration and innovation?
Yeah, there's an upside and downside to really large collaborative teams. The upside is that you have a lot of really brilliant people, and um, these, as I mentioned a couple times, these are really hard missions. So having a lot of brilliant people in one place is great. The downside of having a lot of brilliant people in one place is that a lot of brilliant people usually have a lot of their own ideas. So you tend to have a lot of cooks in the kitchen, as it were, which is not always the most efficient for making progress, but it is the best for ensuring that the mission's going to work. If you look at NASA's track record of these really large missions, they pretty much all work. So it's not fast and it's not cheap, but it's very effective at making a good mission.
Thank you. Uh, Again, a question for Daniel. What habits or routines help you to stay creative and focused when solving highly complex problems?
Yeah, a lot of what I do is you can't see it from here, but I have a whiteboard right there that is where I keep all of my tasks. So I have all of my tasks broken into the main goals and then a bunch of subtasks under them. So that's how I keep track of all the little bits and pieces that I need to do. Because when you have a really big problem, it's very stressful to tackle it all at once. And identifying smaller chunks for yourself helps you to have easier ways to proceed.
Thank you. I have another question. Are there any open source tools or educational resource you recommend for students interested in optical design and space instrumentation?
So if you're members of SBIE and Optica, student chapters can get access to a lot of like SBIE's field guides for free. So there's a lot of good resources there. There's a lot of other textbooks that the societies have that as members you get discounts on. Um, if you go to these conferences, I've there's often workshops for helping students get involved in these kind of things. I've done some workshops with SPAE the last few years, or I did one at Frontiers in Optics this year as well. Um, so yeah, staying involved in the societies is the best way to get access to these kind of resources for free or heavily discounted, at least.
Thank you. Wilmer say, what were some of the most challenging optical design problems you faced on this project and how did you overcome them?
So some of the probably one of the more challenging ones was the low 0.05% uniformity requirement, because the onboard calibration thing does not really have a precedent to this level of accuracy. And so we had to do a lot of work to show that this was going to work out. So the way we overcame it was that we bought a bunch of different potential diffusers and we tried them in the lab. And then my colleague Eric Frater, who sat in my role as design and analyses prior to me, started that process, and I carried it through of evaluating these different components and then down selecting it and then doing a whole bunch of work to prove that this is going to meet its requirements and be able to go to space. So again, it's a lot of like, well, we have this problem, and the only way to see if it's going to work is to try things.
Thank you. Um, how does the instrument's ability to switch between imaging and slitless spectroscopy help astronomers make new discoveries?
Right. So the slitless spectroscopy mode, when it's in use, and I didn't talk about that as much because that's NASA's main contribution, but the way that that works is that instead of like this image on the screen right now that has all these nice galaxies and stars and stuff, you'll have a whole bunch of streaky lines because the prism and the grism elements will spread out spectrally each of these objects into a spectrum on the detector. So the imaging modes gives us more traditional pictures as to what the universe looks like. And the spectroscopy mode is used to help discern what is actually in those stars and whatnot. So they kind of have to work together, because if you just had the spectroscopy mode, you just have a whole bunch of streaky lines and would kind of have a hard idea of what you're looking at. But the imaging mode, because it's looking over hundreds of nanometers, wouldn't give you nearly the specificity that scientists need to measure these. So for a lot of these missions, they're working in tandem.
Thank you, Dr. Ben. Have another question. Have you had a mentor or role model who significantly influenced your career? How did they guide you?
Yeah, I've been very fortunate to have a good number of mentors. The guy who was the optical sciences or the optical systems lead on the mission, Joe Sullivan, when he retired, he had over 45 years of experience in the aerospace industry and had worked on all of those great observatories that I listed off to you. So what an incredible wealth of experience. I think one of the main useful things that I got out of Joe was knowing how to pick your battles from a technical standpoint, and um, how to know when something's really going to be a problem or not. Because it's very easy on these missions to treat every potential problem as it's like the biggest possible problem, because unless you study it, it's hard to know. But everything that you do for your customer does cost your time, which costs your company money. And so you have to kind of choose, like, we want to be good partners with our customer and support their requests, but we can't do all of this stuff because we've contractually agreed to a certain scope of work and we don't want to expand that unnecessarily. So he was great at doing that. He was great at learning how to deal. When you're a student, you don't really have this relationship with a contractual relationship with other people, and so learning how to navigate that was very useful from Joe's perspective.
Thank you. What inspired you to specialize in optical engineering for a space telescope, and how did your PhD shape your career path?
So originally, I got interested in space telescopes as a kid from the space shuttle. I had a bunch of different. This is gonna date me, but I had a whole bunch of VHS tapes that I watched as a kid. And one, there goes the police car, there goes a fire truck, and there goes a space shuttle. And the space shuttle one was always the coolest one to me. All that space stuff just seemed so awesome. And that's kind of the spark of what got me interested in doing space work specifically. I didn't go into optics intending to do space specifically, but I'm very grateful that I ended up here because I love living in Colorado for one, and it's really cool to make space telescopes. As far as how did my PhD career or shape my career path, um, I think the thing that you don't really appreciate about a PhD until you're on the other side of it is that getting a PhD gives you a lot of mental resilience. And because when you're a PhD student, you frequently have the experience of, well, I don't know how to do this, but I looked online, turns out nobody knows how to do this. So I guess I have to be the one who figures it out and writes the paper about it. So um, that is very influential to helping you to have the resiliency to push through these complex problems. The other thing that my PhD did is it really gave me the joy of doing hard research, which the stuff that we're doing for the Habitable Worlds Observatory right now, I'm one of the leads on that research effort. And it's really, you don't really realize R&D seems like really scary from the outside of doing R&D because you're constantly doing stuff that nobody knows how to do. But man, it's exciting when you figure it out. That first time when you get that result to work, like you get hooked on that. And I think my PhD helped me to get hooked on that.
Thank you, Ben. And another final question. Working on a NASA flagship observatory must involve teamwork across multiple disciplines. What skills have been most valuable for collaborating effectively in such large projects?
Yeah, that's a very intelligent question. So it's absolutely very true. So the challenge that we face as optics people is that we are the magic wizards of the engineering world, because the odds that you know some things about mounting and holding stuff, or you know some things about electronics from using a detector, are decent. But the odds that that electronics person knows anything about optics, or that mechanical person knows anything about optics, are very poor. So you're constantly facing this battle of being like, okay, I have to somehow get across that this laser interferometer just magically knows from shooting light out how good the optic is. I have to explain that to the mechanical person. Um, so yeah, it's tricky. I think a lot of what you as an optics person have to be able to do is you have to learn to flex into their discipline more than they're going to have to learn how to flex into yours, because it's just a lot. It's a lot easier for us to expand out of optics than for most other engineers to expand into optics. So, knowing a little bit of SolidWorks in my case is very helpful for talking to the mechanical engineers, because then I can ingest their models, I can look at it, I can give feedback on it. Knowing how to talk a little bit about noise is very helpful for talking to the electronics people when I'm talking about detectors and whatnot. So, um, they say to be a great engineer, you kind of need to be T-shaped. You've got to have a breadth and a depth. And being an optical engineer, you definitely have to have some of that breadth into other disciplines to be useful in these big collaborations. It takes patience, it takes time. You'll pick it up over your career, so I wouldn't fret about it too much.
Thank you, Dr. Ben, for response all those questions. And thank you again so much for your excellent talk. It has been really interesting to learn about everything have you share and what you accomplished working on these projects. We hope to have you back another event very soon. Thank you.
Thanks so much for having me. Take care.